Okay, this is part 2 of Unit 11B, and we are looking at perspectives and symmetry. And the first video, we kind of gave you some history, some ideas of perspective in drawings, and so now here's a problem that we can look at. So in this case, we've got figure 11.33, which is this picture right here. Shows two poles drawn with correct perspective relative to a single vanishing point. Our vanishing point would be out here. And then, so it says, as you can check, the first pole is 2 centimeters tall in the drawing, and the second pole is 2 centimeters away. Now, this is pulled from a textbook, so this may not be exactly to scale. But basically what we're saying is this is 2 centimeters tall, and then when we go along the ground here, this is also 2 centimeters. But again, if you get out and measure those, this is pulled from a textbook, and I've resized it so it's not going to match that perfectly. And then the second pole, it says, is 1.5 centimeters tall. And wants us to draw 2 more vertical poles with the correct perspective that are equally spaced along the baseline of the drawing. Assume the poles are of equal height in the real scene. So, and if you're doing this and you had this picture, you would have not that line, but you'd have a line. I'm going to try and get this best without a ruler here. Get my perspectives off, but essentially you'd have a line. I'll just kind of aim right in the middle here. You'd have a line that would go from peak to that point, and then you'd come out another 2 centimeters, and you would draw your post. So this would be 2 centimeters here, because it's asking them to be, in this drawing, it's asking you to draw them 2 centimeters. So you'd get something like this. And if you want a better representation, there it is right there. It's generated by a computer, but there's kind of the basic idea of where you'd get that. Then estimate the heights of the 2 poles that you've drawn. You would actually just have to get out, because we're given some numbers, but we're not given sufficient information. We would actually need this angle right here or some other information to get the precision and to be able to mathematically calculate these, but you can just get out a ruler and measure those. In your homework assignment, you'll see it on the picture will be created something like this down here before you, and you'll just need to measure these heights right here. But the heights, when I measured it and did it out, this was about 1.3. Sorry, that color's not very good right there. This was about 1.3 centimeters high, and then this other guy was about 1 centimeter tall. Again, you're going to get some estimates here, round to the nearest tenth of a decimal place. And then question C, in the actual sense, would these 4 poles be equally spaced? And actually, the answer is no on here. Based off of the actual scene and your perspective here, they would actually be. So I would say the spacing would be greater as you got further and further away from that first pole, and the heights would be smaller. So the spacing would be greater and the heights would be smaller. And this would be based off of your perspective, looking at this kind of from a higher vantage point. If you were imagine yourself standing up on a hill and looking down at this. The spacing would, the 2 centimeters here, this is just to make things more simplified, but in reality, they would look, it would become a greater distance between the poles as you get farther and farther down. Yeah, so that's the idea of perspective. Now we're going to change gears. We're going to go into symmetry. And with symmetry, this should be something you should have heard of before. So symmetry is basically the property of an object that remains unchanged under certain operations. So again, unchanged under certain operations. So for example, a circle looks the same if it is rotated about the center. You can't differentiate the circle if you kind of pin down the center point and start rotating it. It will look the same. A square looks the same if you flip it across one of its diagonals. So if you imagine this, drawing this dotted line and then from there flipping it around, it's going to look like the same square. So that's the idea of symmetry. Some mathematical symmetries are really subtle, but we're going to talk about 3 symmetries that are easy to identify. The first is reflection symmetry. And that's just, imagine if you draw a dotted line here, if you were to reflect or flip it over that dotted line, the figure would look exactly the same as it was in the beginning. You wouldn't be able to differentiate between what was the first and the second look. Some have multiple lines of symmetry. So A only has 1 line of symmetry that cuts right down the middle. But H actually has 2 lines of symmetry. You could cut it in half this way and reflect it across that line, or you could cut it horizontally this way, reflect it across that line. Either way, you wouldn't be able to determine, which was the first, which was the second, and so forth. So that's the idea of reflection. Rotational symmetry. So an object has rotational symmetry if it remains unchanged when you rotate it through some angle and a point. So the angle is important, and then the point is also important as well. So if we look at our letters, O has rotational symmetry, S also has rotational symmetry, and both of them would remain unchanged after a 180-degree rotation. You wouldn't be able to determine which was the first rotation, which one didn't have a rotation. Okay, translational symmetry is a pattern that shows translation. So translation means you just physically move the object from side to side or up and down and so forth. So we sometimes call these shifts. So again, they look the same when you're translating around, and they maintain the same translation symmetry means you maintain the same shape, same size, same orientation, and so forth. And in math and physics, translating means you move it in a straight line without rotating. So you can go in a straight line this way and then a straight line vertically. But we're not going to be doing any of this kind of stuff where you go along a diagonal. We're going to go horizontal shifts and vertical shifts for our translations. So if we look at this, find all the capital letters of the alphabet that have the following: right to left symmetry, such as A. So that was where you could cut it down the middle and then go, imagine flipping it right to left. So you probably want to get your alphabet in front of you and just go through and look. But A has it, H has got it, I has got it, M, O, T, and then several at the end, capital U, V, W, X, and Y. So you have several that have this right to left reflection symmetry. Now top to bottom, not quite as many. A definitely does not have it, but B's got it. C also does. D, E, F unfortunately has something different on the bottom, so it doesn't go the same, but H works, I works, and then we have to go to K, and then to O, and then X. And those are the only ones that have top to bottom symmetry. So that's if you were to draw a line kind of cutting through this way and reflect across that. You know, which ones have both left and right, top and bottom? If you look here, you know, the kind of the overlaps that we have H is in both of the first two parts, I is in both the first two parts, O is in both of them, and as well as X. So that's our reflection symmetry. Now, which ones have rotational symmetry, where you could rotate at a certain angle and not be able to differentiate? So H and I, again, are popular ones. Those, you can rotate those 180 degrees. N, you can also rotate that 180 degrees. O, S, as we mentioned before. X, and then Z also. So those are all of the letters, uppercase letters of the alphabet that have rotational symmetry. Just check my time here. Okay. Now, the rotational symmetry doesn't have to necessarily stick to letters. We can go to geometric figures. So in one case, you know, we have an equilateral triangle where all the sides are the same. How many degrees can the triangle be rotated about its center and remain unchanged in its appearance? So if we're fixated on the center, that point doesn't move, and we just start rotating this thing around. Well, imagine at some point this is going to rotate and land right here. So there'll be one. There'll actually be two different places where this can happen. And so, you know, and then finally we can get back to the beginning. So what we can do is we can take 360 degrees, and if we divide that by 3, that will give us 120 degrees. And that turns out to be the angle at which we need to rotate this thing in order to get symmetry, the rotational symmetry here. So you would be 120 degrees, and then you could also go 240, so it would be 120, 240, and then obviously 360, but you're back to the original. And then you could keep going. You could say 360 plus 120, 360 plus 240, and keep going around. But these are the two that are under 360 degrees. Same thing with the square. You could rotate here. There's once, twice, and 3 different times, so 3 different ways, and then your full circle will take you back. But there'll be 3 different objects, so in this case we'd take 360 and divide it by the 4 corners, which is 90 degrees. So this one occurs at 90 degrees, 180 degrees, and 270, and then you'll be back to 360. So there are 3 different possibilities on this one. Okay, and then on a pentagon, same idea. This time there are 5 little corners, so you're going to be rotating 5 times. So you're going to take 360 and divide it by 5, and this gives you 72 degrees. So it'll be at 72, and then 72 plus 72 is 144, plus 72 again is 216, plus 72 again is 288 degrees, and then plus 72 gets you back to 360. So hopefully you can see a pattern there that those rotational symmetries are, you take 360 and divide it by the number of sides, and that will give you the degrees. We'll answer part D on the next video as I'm running out of time.